Imagine for a moment that you are holding a coin in the palm of your hand, and you gently toss it into the air. Watch as it spins rhythmically under the soft glow of the lamp. Eventually, it falls, heads or tails. You might believe that the result was determined the very instant it left your fingers, and that you simply did not know the outcome yet. However, there exists a strange and hidden world where that coin does not choose a side until the very second you look at it. It is even more fascinating than that. While it floats in midair, unobserved by anyone, it is simultaneously heads and tails. It is not one or the other, but truly both at once. This concept may sound difficult to grasp, but this is the realm we are about to enter together tonight. I invite you to contemplate 3 profound questions. First, consider the moon hanging in the night sky. Does it truly exist when you are not looking up at it? Or does it only appear when there is an observer? Second, think of a tiny speck of dust, smaller than what you see dancing in a sunbeam. Is it possible for it to be in 2 different places at the exact same time? And finally, does the reality in which we live depend on whether or not we have our eyes open to witness it? These inquiries might seem illogical, defying everything we have learned since childhood. Yet, this is precisely what science has uncovered over the last century. Tonight, we will explore the strangest world humanity has ever found. A place where everything you think you know about reality could be entirely wrong. This world is not on Mars, nor hidden in science fiction novels. It is right here, in every atom that makes up your hand, and in every ray of light that touches your eyes. This is not imagination, but real science, proven by thousands of experiments. Welcome to Study and Sleep, where we explore the universe's deepest ideas in the most gentle and soothing way possible. Whether you are resting in bed, sitting on your sofa, or on a train ride home, please find a comfortable position, because tonight's journey will completely change how you view the world around you. Let us travel back in time to more than 120 years ago, at the dawn of the 20th century. At that time, scientists were living in a golden age of confidence. They believed they had nearly understood everything about the cosmos. Isaac Newton, with his famous laws of motion, had explained why an apple falls to the ground and why planets orbit the sun. Maxwell, a genius from Scotland, had written beautiful equations explaining light and electromagnetic fields. Everything fitted together like perfect puzzle pieces. Thermodynamics, mechanics, and electromagnetism were all neatly arranged in thick textbooks. Some prominent scientists of that era even declared that physics was nearly complete. They said there were only a few minor details left to tidy up, like sweeping a few specks of dust from the corner of a room. Some even advised young students not to pursue physics, believing all the great questions had already been answered. But they were wrong. They were profoundly mistaken, because in those tiny dark corners, within those seemingly insignificant details, lay secrets that would completely overturn our understanding of reality. Just a small issue concerning light and heat was enough to bring down the entire castle of knowledge that had been built over centuries. The problem began with something very simple. When you heat an object, it glows. You can see this everywhere. An iron bar placed in a forge turns from black to red, then orange, then yellow, and finally a brilliant white as the temperature rises. A burning candle emits a warm yellow light. The filament bulb in your home works on this exact principle. Electricity heats the metal wire until it shines. This phenomenon is so common that everyone knows it. However, when scientists tried to explain exactly why this happens, they encountered a terrible problem. According to the classical equations they trusted, as an object's temperature increases, it should emit more and more energy at shorter wavelengths. This sounds reasonable until you calculate it further. The math stated that at very short wavelengths, like ultraviolet rays, the amount of energy emitted would increase to infinity. Infinity. Do you understand the implication of this word? It means a tiny piece of coal, when heated, would release more energy than the entire universe combined. Your home heater would become a source of endless power. Everything would glow with blinding brilliance and unimaginable radiation. Naturally, this is completely absurd. In reality, your heater does not destroy the universe. The coal simply emits a moderate amount of light, warm and unremarkable. But the mathematics, the very math that scientists had trusted for hundreds of years, said something entirely different. Scientists tried everything. They tweaked equations here and adjusted variables there, checking every calculation step. But no matter what they did, that terrifying infinite number kept appearing like an unbreakable curse. This problem was even given a dramatic name: the ultraviolet catastrophe, because it occurred in the ultraviolet region of the light spectrum. For years, no one knew what to do. Then, in the year 1900, a German physicist named Max Planck entered the story. Planck was not an adventurer or a revolutionary. He was a careful and conservative man who believed in classical principles. He had no desire to break anything. He only wanted to fix that annoying equation. Planck spent months struggling with the numbers. He tried every approach. Finally, in a moment of desperation, he decided to try a completely radical idea. He asked himself, what would happen if energy could not be emitted in just any arbitrary amount? What if energy had to arrive in small, discrete packets, much like coins? Think about it. You cannot have half a coin. You cannot have a third of a coin. You can only have 1, 2, or 3 whole numbers. Planck proposed that energy behaves the same way. It cannot flow continuously like water. Instead, it must jump in tiny steps, just like climbing stairs, where you take one step at a time and cannot stop between 2 steps. He called these smallest packets of energy quanta. He even calculated the size of these packets using an incredibly small number, which today we call Planck's constant. When Planck inserted this idea into his equation, a miracle occurred. That terrifying infinite number vanished. The equation began to yield reasonable results. Even more than that, they matched perfectly with what was measured in real experiments. The problem was solved, and the ultraviolet catastrophe was averted. But Planck was not happy with his own solution. He viewed it merely as a mathematical trick, a cunning way to make the numbers look better. He did not believe that energy actually arrived in discrete packets. He thought surely someone would find a better explanation, one that did not require such strange assumptions. He was wrong. He did not know that he had just opened the door to an entirely new world, a world where everything we take for granted would be challenged. While Planck worried about his energy packets, another mystery was waiting to be solved. This time, it involved light, metal, and tiny particles called electrons. It had long been known that when you shine light onto a metal surface, sometimes electrons are kicked out of that surface. This seems simple enough. Light carries energy, transfers it to the electron, and once the electron has enough energy, it flies out. Easy to understand, right? But when scientists experimented more carefully, they discovered something very strange. According to classical wave theory, if you increase the brightness, meaning you make the light stronger, the electrons should fly out with greater energy, just as stronger water waves push a boat harder. But in reality, that is not what happened. No matter how blindingly bright the light was, the electrons still flew out with the same energy level. The only thing that mattered was the color of the light, or more precisely, its frequency. With red light, no matter how bright it was, the electrons would not budge. But with violet light, even a dim faint ray would cause electrons to pop out immediately. It was as if there was a locked door. You could have a million wrong keys, but they would not work. Yet just one correct key would open it instantly. This did not fit with the wave theory of light at all. In 1905, a young man working at a patent office in Switzerland decided to solve this problem. His name was Albert Einstein. At only 26 years old, Einstein had read Planck's work. He pondered those strange packets of energy. Then he had a bold idea. What if light does not just carry energy in packets, but light itself is made of discrete energy packets? In other words, what if light is not a continuous wave, but a stream of tiny energy bullets flying at the speed of light? Einstein called these bullets light quanta. Later, they would be known as photons. Each photon carries a specific amount of energy depending on its frequency. Violet light photons have high energy, while red light photons have low energy. When a photon strikes an electron in metal, it gives all its energy in a single hit. If the photon has enough energy, the electron escapes. If not, then even a billion such photons hitting it will fail to release the electron. This explained perfectly why color mattered more than brightness. Brighter light just means more photons, but if each photon is too weak, more of them won't help. It is like having a million plastic hammers versus one iron hammer to break a concrete wall. Einstein's idea matched experiments perfectly. Before we continue to the next part of this fascinating history, take a moment to breathe deeply with study and sleep. Einstein's discovery raised a difficult question. What is light? Is it a wave or a particle? For hundreds of years, it was proven to be a wave. Now Einstein said it was a particle. The answer he offered was even stranger. Light is both. Depending on how you look at it, it reveals a different face. And this duality was just the beginning. Einstein received the Nobel Prize in 1921 for this work, not for his famous theory of relativity, but specifically for discovering the quantum nature of light. The scientific world began to realize they were standing before something entirely new and utterly alien. If light could be both a wave and a particle, what about everything else? Is reality playing by rules we have never imagined? To find the answer, we need to look at one of the strangest, simplest, yet most profound experiments in the history of science. An experiment requiring only 2 tiny holes in a card, yet capable of shaking the very foundations of reality. Let us discuss this experiment. It is not the kind with complex machinery or cutting-edge laboratories. It is so simple that almost anyone could theoretically perform it. You need a light source, perhaps just a flashlight, a thin card with 2 tiny slits cut parallel to each other, and a wall or screen behind it to catch the light. That is all. 3 simple things are enough to create one of the most bizarre discoveries in history. Many famous physicists have called this the most dramatic experiment ever performed. Some even joke that it deserves an Oscar because it has everything: mystery, suspense, unexpected results, and an ending that leaves you sitting in silence, pondering the meaning of life. But before we begin, we need to know what to expect. In the classical world, waves and particles behave very differently. Let us consider two cases. Case 1. Waves. Imagine you are standing by the sea, watching waves crash against a wall that has two openings. The water waves will pass through both holes and spread out behind them. Then, these two groups of waves will meet. Where a wave peak meets another peak, they add up to make a bigger wave. Where a peak meets a trough, they cancel each other out. The result is a striped pattern of alternating strong and weak waves. Scientists call this an interference pattern. Case 2. Particles. Now, instead of water waves, imagine you are throwing tiny marbles at a wall with two holes. Some marbles will fly through the left hole, and some through the right. They do not interfere, nor do they create any special pattern. On the wall behind, you will simply see two piles of marbles concentrated directly behind the two openings. Simple, understandable, and nothing strange. So, what will light do? Will it act like a wave or a particle? Scientists performed this experiment long ago, hundreds of years back, when they shone light through two slits. The result was clear. An interference pattern appeared. On the screen behind, instead of seeing two simple bands of light, they saw multiple alternating bright and dark stripes, exactly like water waves. This seemed to prove clearly that light is a wave. People had known this since the 19th century. Maxwell's equations explained it perfectly. Everything seemed fine until Einstein appeared with the idea of photons, those bullets of light. That posed an uncomfortable question. If light is truly made of discrete particles called photons, then why do they create a wave-like interference pattern? To answer this, scientists decided to do something bold. They lowered the intensity of the light source significantly. They lowered it so much that only one photon was fired at a time. A solitary photon flies toward the two slits, then hits the screen behind, leaving a tiny dot of light. Now, think about this for a moment. We have a single photon. It cannot interfere with another photon because there are no others. It must go through one of the two slits, either the left or the right. According to normal logic, after firing enough photons, we should see two piles of light dots concentrated behind the slits, just like the marbles. But that is not what happened. At first, when only a few photons hit the screen, everything looked random. A dot here, a dot there, with no pattern. But the scientists were patient. They let the experiment run for an hour. Then thousands of photons, tens of thousands, flying one by one through the slits and hitting the screen. Gradually, a pattern began to emerge. The light dots were not distributed evenly. They concentrated into bands. Bright band, dark gap, bright band, dark gap. Exactly like an interference pattern. But how is this possible? Each photon flew alone. It had no other photon to interfere with. So who is it interfering with? The only answer that seems plausible, though it sounds insane, is that each photon is interfering with itself. Somehow, a single photon seems to go through both slits at the same time. like a ghost splitting in two, traveling both paths, and then meeting itself on the other side to create interference. This was already hard to believe, but the strangest part was yet to come. Scientists decided to solve this mystery once and for all. They placed very small, sophisticated detectors right at the two slits. The goal was to see which slit the photon actually went through, the left, the right, or truly both. This device did not do much. It simply observed. It just recorded information. Simple as that. No pushing, no pulling, doing nothing to the photon physically. They turned on the detector and ran the experiment again, firing one photon at a time. Just like before, the interference pattern vanished completely, cleanly gone, as if it had never existed. Instead, on the screen, there were only two simple bands of light right behind the two slits, exactly what you would expect from normal particles. The photon now behaved like tiny marbles. Half went through the left, half through the right. No interference, no wave behavior, no magic. The scientists turned off the detector and ran it again. The interference pattern returned, beautiful as ever. Turn the detector on, pattern disappears. Turn it off, pattern returns. On, gone, off, back. They repeated this many times, and the result was always the same. When no one is looking, the photon acts like a wave, creating a magical interference pattern. When there is an observing device, even if that device does not disturb the photon in any physical way, the photon immediately decides to act like a normal particle. This is unlike anything that happens in our ordinary world. When you do not look at a car parked on the street, the car is still there, in the same spot. Whether you look at it or not does not change its location. But at the quantum level, things are different. The behavior of the photon, whether it acts as a wave or a particle, seems to depend on whether we are observing it or not. It is not because the measuring device messes it up. Scientists designed extremely sensitive detectors that barely interact with the photon, yet the result remained the same. The issue is not how we observe, but the very act of observation itself. The universe at its deepest level seems to care if anyone is watching. Some scientists describe it like this. When unobserved, the photon exists in a state of ambiguity, a cloud of possibilities, something spreading across multiple paths at once. It has no specific position, no specific path. It is all possibilities simultaneously. Only when we measure, when we look, does that cloud of possibilities collapse into a specific point, a specific path, a specific reality. It is as if the universe is in an undecided state until someone asks it a specific question, and only then is it forced to give an answer. This experiment has been repeated thousands of times in hundreds of different labs by thousands of different scientists. They tried it with photons, with electrons, and even with larger molecules consisting of hundreds of atoms. The results were always the same: unobserved, wave behavior, interference, spreading across paths, observed, particle behavior, one specific path, no interference. This is not a machine error. It is not human error. This is simply how reality works at the quantum level. Some find this terrifying. It means reality is not as solid as we think. It is not predetermined. It does not exist independently of our observation. To some extent, our act of observation is part of creating reality. Others find it beautiful. It means the universe is more flexible, more open, and full of possibilities than we ever imagined. It is not a rigid clockwork machine running on preset rules. It is something more alive, responsive, and strange. The double-slit experiment offers no easy answers. Instead, it poses deeper questions. What is observation? When is reality defined? Is everything just a possibility until we look at it? What role do humans play in this universe? These questions are not empty philosophy. They are raised by concrete experiments, carefully measured, and repeated countless times. This is science. But science has pushed us to the edge of understanding, where science meets philosophy, where the question what meets the question why. The double-slit experiment tells us one thing for sure. The universe is not a simple clockwork mechanism. It is a tapestry woven from possibilities, something shimmering, changing, and responding to our gaze in ways we still do not fully understand. Photons wink at us when we look away, then stand still when we look back. The universe is playing a game with us, a strange, mysterious, but endlessly fascinating game. So what is really happening here? How can we describe a world where everything is a possibility until observed? How can mathematics capture the maybe instead of the definite? To answer those questions, we need a new tool, a new equation, a new way of thinking about reality, a perspective that speaks not of what things are, but of what they become. That is when an Austrian physicist named Erwin Schrödinger entered the story, with an equation that would change everything. In 1926, Schrödinger sat in a small room in the Alps, contemplating the strange problems the quantum world was presenting. He knew electrons did not act like marbles. They created interference patterns like waves. They appeared in unexpected places. They seemed to spread through space in ways classical physics could not explain. He needed an equation that could describe not where the electron is, but where at times could times be. Not certainty, but possibility. Not a point, but a cloud. After weeks of tireless work, Schrödinger wrote down a beautiful, elegant equation. It was not long or visually complex, but what it described was completely revolutionary. You do not need to understand math to grasp the core idea. In fact, Schrödinger himself was not entirely sure of the philosophical meaning of the equation he had just created. But the equation worked. It predicted exactly what experiments measured. That was the most important thing. At the heart of Schrödinger's equation lies a concept known as the wave function. Scientists often denote it with the Greek letter psi, which looks a bit like a small trident. The wave function is not something you can see or touch. It is not a physical wave rippling on water or through the air. Rather, it is a mathematical tool, a way to describe everything we could possibly know about a quantum system. To understand the wave function, let us imagine a scenario. You are standing in a dark room, blindfolded. Somewhere in this room, there is a cat. You do not know where it is. You gently toss a small ball, listening for the sound if it hits something. You toss another ball. One by one, you gradually build a mental map of where the cat might be. Some areas seem highly likely. Perhaps the cat is resting there. Other areas seem unlikely. Surely it is not in that corner. You do not know for certain, but you have a picture of probability. That is exactly what the wave function is. It does not tell you where the electron is. It tells you that the electron has a high probability of being here, a low probability of being there. and is almost impossible to be over yonder. It is a probability map of every place the particle might appear. The wonderful thing about Schrödinger's equation is that it allows us to calculate how this wave function changes over time. Just as you can predict how a ripple of water will move, Schrödinger's equation allows us to predict how the wave of probability will spread, shrink, or fluctuate. But something very strange happens when we measure it. While the wave function is progressing smoothly, spreading through space like mist, everything is fluid, continuous, and predictable. The electron exists as a cloud of possibilities, a little bit here, a little bit there, everywhere at once in varying proportions. Then you measure it. You place a detector, and you look immediately, not gradually but instantly. That entire cloud of probability contracts into a single point. The wave function collapses. The electron is suddenly in one specific place, no longer everywhere. It is like a flash of lightning in the dark night. A sudden beam illuminates a hill while everything else remains in fog. Before the measurement, the electron could be at A, could be at B, or could be at C, all simultaneously to different degrees. After the measurement, the electron is at B, definite and clear. All other possibilities vanish. This is unlike anything in classical physics. In the ordinary world, if you do not know the location of an object, it simply means you lack information. The car is still in a specific spot. You just do not know it yet. When you look, you do not change the car's location. You only acquire new knowledge. But in the quantum world, before measurement, the electron truly has no specific position. It is not hiding somewhere unknown. It is genuinely a cloud of possibilities. The act of measurement does not just reveal information, it creates the result. Schrödinger's equation is not just a beautiful theory. It explained things that classical physics could never resolve. Take the hydrogen atom, the simplest atom in the universe, consisting of just one proton and one electron. For decades, scientists could not understand why the electron did not crash into the proton. According to classical physics, the electron orbits the nucleus like a planet orbits the sun. But an electron carries a charge, and a moving charged object must emit radiation, lose energy, and eventually spiral into the nucleus. Every atom should collapse in the blink of an eye. But that does not happen. Atoms are stable. Why? When Schrödinger applied his equation to the hydrogen atom, something beautiful emerged. The electron is not a tiny particle orbiting the nucleus. Instead, it is a standing wave, a stable vibration pattern surrounding the nucleus, much like sound resonating within a bell. These patterns create regions where the electron can exist, not clear orbits like planets, but clouds of probability. Scientists call these orbitals. You may have seen images of them in textbooks. Strange shapes like dumbbells, hourglasses, or flowers. Those shapes are not just illustrations. They represent the places where the electron is most likely to be found when you look. The electron is not at a specific point. It is spread out across that entire region like a cloud. Schrödinger's equation became the foundation of modern chemistry, materials science, and semiconductor technology. The computer you are using, the phone in your pocket, all work thanks to predictions from this equation. However, Schrödinger's equation also revealed something unsettling. It showed that there are fundamental limits to what we can know. a year after Schrödinger published his equation. In 1927, a young German physicist named Werner Heisenberg discovered something shocking. He realized there is an absolute limit built into the very structure of the universe regarding how precisely we can know things. Specifically, Heisenberg found that you cannot know both the exact position and the exact velocity of a particle at the same time. It is not because your measuring instruments are not good enough. It is not because you are not clumsy. It is because the universe does not allow it. This principle has a simple mathematical formula, but profound consequences. It states that the uncertainty in position, multiplied by the uncertainty in momentum, must always be greater than or equal to a tiny number. What does this mean? It means if you know very precisely where a particle is, you cannot know precisely how fast it is moving. Conversely, if you know its speed very precisely, you cannot know where it is. As one becomes clearer, the other becomes blurrier. This is a trade-off of the universe, a balance built into the fabric of reality. There is a wonderful way to visualize this. Imagine you are trying to hold fog in your hand. If you open your hand wide, the fog spreads out. You have more fog, but you do not know exactly where it is within your palm. If you squeeze your hand tight, trying to pinpoint its location, the fog escapes through your fingers, and you lose it. The harder you try to hold it, the more you lose. That is exactly how the universe works at the quantum level. You cannot catch an electron and say, "Here it is, right here," moving at exactly this speed. The universe does not permit such absolute certainty. Heisenberg's uncertainty principle is not just a mathematical curiosity. It has profound practical consequences. In fact, it explains why you exist. Let us return to the old problem. Why doesn't the electron fall into the nucleus? The electron carries a negative charge and is strongly attracted to the positively charged nucleus, like an apple attracted to the earth. In principle, the electron should fall straight in. But the uncertainty principle prevents this. If the electron fell into the nucleus, it would be confined in an incredibly small space. Its position would be known very precisely. According to the uncertainty principle, when position is extremely precise, the uncertainty in velocity becomes massive. In this case, it would become infinitely large. The electron would have to be capable of moving at every possible speed, from standing still to near the speed of light. That would require a colossal amount of energy, practically infinite. The universe says, no, energy cannot be infinite. Therefore, the electron cannot crash into the nucleus. Instead, it must hover at a certain distance. Within those probability zones we call orbitals. The uncertainty principle creates a quantum pressure, a force pushing back against confinement. It keeps the electron from being trapped too tightly. It maintains the stability of the atom. It is the reason matter does not collapse into an infinitely dense lump. Without the uncertainty principle, you could not exist. There would be no stable atoms, no molecules, no chemistry, and no life. This uncertainty, which might sound like an annoying limitation, is actually one of the most essential features of the universe. Many people, when hearing about the uncertainty principle for the first time, find it disappointing. They think it means we simply cannot know things precisely. It sounds like a failure, a human limitation. But that is not what Heisenberg discovered. He was not saying our measuring tools are insufficient. He was saying that no measuring tool, no matter how perfect, can overcome this limit. Because this limit is not in the machine, it lies in the nature of reality. Particles do not have a precise position and a precise velocity at the same time, not because we do not know, but because they do not possess them. The concept of a particle being exactly here, moving at exactly this speed, has no meaning in the quantum world. Some philosophers even find this liberating. It means the universe is not a rigid clockwork machine where everything is predetermined. There is flexibility, openness, and space for novelty. The uncertainty principle allows for miracles like quantum tunneling, atomic stability, and the entire richness of chemistry. Without it, the universe would be stiff, boring, and dead. So perhaps, instead of feeling sad that we cannot know everything exactly, we should marvel that the universe leaves a little room for surprise, for possibility, and for the beauty of uncertainty. Now that we have Schrödinger's equation describing the world as a cloud of possibilities, and the uncertainty principle stating that absolute certainty is impossible, all of this leads to a larger, stranger question. If particles are not in a specific place and do not have a specific velocity, then where are they? What are they doing? Let us return to the coin we mentioned at the beginning of this video. In the ordinary world, when you toss a coin into the air, it will always land on one of two sides, heads or tails. You might not know the result beforehand, but you are certain of one thing. From the moment it left your hand, it was already decided. The physics of rotation, the angle, the force, all predetermine the outcome. That is a classical coin. Now, imagine a quantum coin. This coin flies into the air, but instead of being heads or tails while flying, it exists in a strange state, both heads and tails at the same time. Not either this or that, not undecided, but truly both. Only when the coin lands, when you look at it, when you observe, then, and only then, does it choose a side. Before that, it was genuinely a mixture of heads and tails in a way our brains cannot visualize. Physicists call this quantum superposition. This is the core concept. The weirdest part of the quantum world. At the smallest level of the universe, things do not have to choose a single state. They can be in multiple states simultaneously until someone or something forces them to choose. An electron can spin clockwise and counterclockwise at the same time. A photon can travel path A and path B simultaneously. A particle can be at position X and position Y in the same moment. This is not poetry. This is not a metaphor. This is reality, measured and verified thousands of times in laboratories. In 1935, Erwin Schrödinger, the very man who wrote the wave function equation, sat pondering the implications of these discoveries. He felt uncomfortable. Quantum superposition might be acceptable for tiny particles, but does it apply to larger objects? To demonstrate the absurdity of applying quantum rules to the macroscopic world, he devised a thought experiment. This experiment later became so famous that almost everyone knows it, even if they have never studied physics. The experiment goes like this. You place a cat inside a sealed box. Beside the cat is a tiny radioactive atom, a detector, and a vial of poison. The mechanism is simple. If the radioactive atom decays, the detector detects it, triggering a hammer that breaks the poison vial, and the cat dies. If the atom does not decay, everything remains normal, and the cat lives. Now comes the quantum part. According to quantum mechanics, the radioactive atom exists in a state of superposition, both decayed and not decayed, until it is observed. That means the entire system, the detector, the poison vial, and even the cat, must be in a state of superposition. The cat is both alive and dead, not alive or dead, and we don't know yet, but truly both alive and dead at the same time, until someone opens the box to look. Schrödinger offered this example not because he believed it was true. On the contrary, he wanted to point out the absurdity of applying quantum rules to large objects. He wanted to say, hey, look what crazy things happen if we believe. Big things act like quantum things. But this paradox became too famous. It became the symbol of quantum physics, appearing on t-shirts, in movies, and comics. Schrödinger's cat is now how everyone talks about quantum uncertainty. The real issue this thought experiment raises is somewhere between the tiny atom and the large cat, between the quantum world and the classical world. Where is the line drawn? Why can an electron be in two places at once, but a cat cannot? This question still does not have a completely satisfying answer. But interestingly, the principle of superposition is not just empty theory. It is being used in real technology right now. The conventional computer you use every day operates on numbers known as bits. Each bit can only be a 0 or a 1, much like a light switch that is either off or on. Computers process billions of these bits at dizzying speeds. But ultimately, each bit remains just a 0 or a 1 at any single moment. Now, scientists are building an entirely new kind of machine called a quantum computer. Instead of bits, they use quantum bits, or qubits. A qubit can be not just 0 or 1, but it can be both 0 and 1 simultaneously, thanks to quantum superposition. This might sound like a minor change, but the consequences are massive. One qubit can store 2 values at once. 2 qubits can store 4 values. 3 qubits can store 8 values. The numbers increase exponentially. With just a few dozen qubits, you could perform calculations that would take a normal computer thousands of years to finish. Of course, building a quantum computer is incredibly difficult. Qubits are very fragile. They are easily disturbed by everything around them, such as temperature, vibrations, or even light. Once disturbed, the superposition collapses, and the quantum bit reverts to a normal classical state. Yet, despite the difficulties, scientists are gradually moving closer to building truly useful quantum computers. Quantum superposition, that thing which sounds like science fiction, is becoming real technology. Superposition is strange enough, but the quantum world holds an even stranger phenomenon, a phenomenon that made even Einstein, the man who revolutionized physics, shake his head in refusal. Imagine you have a pair of gloves, one left and one right. You place each one into a separate box, then send one box to Paris and the other to Tokyo. When you open the box in Paris and see a left glove, you immediately know the box in Tokyo contains the right glove. This is completely normal. Nothing strange here. The information was determined from the start. You only learned it when you opened the box. But quantum entanglement is entirely different. When two particles become entangled with each other, usually because they were created together or interacted. They do not decide their states in advance. Like the quantum coin, they exist in a state of superposition, but their states are linked in a bizarre way. When you measure the first particle, it chooses a state, say, spinning up, instantly, no delay, no signal required. The second particle, even if it is thousands of kilometers away, knows immediately. It will choose the opposite state, spinning down. Nothing travels between the two particles. No radio waves, no signals at all, not even a time delay. This connection happens instantaneously, regardless of distance. Einstein called this spooky action at a distance. He hated it. He believed that nothing, including information, could travel faster than light. That was one of the fundamental principles of relativity, the theory he himself had created. He argued that there must be hidden variables, secret information carried by the particles from the start, just like the two gloves in the boxes. Quantum theory is incomplete, he said. It is missing something. For decades, quantum entanglement was merely a philosophical debate. But in the 1960s, an Irish physicist named John Bell did something extraordinary. He found a way to test if Einstein was right. Bell wrote down a mathematical inequality, a kind of formula that allowed us to distinguish between two scenarios. 1. Einstein is right. There are hidden variables. 2. Quantum theory is right. Entanglement is real. Scientists performed the experiment. They created pairs of entangled particles, measured them, and checked the numbers. The experiment was repeated thousands of times in dozens of different labs. The results were clear. Quantum theory is correct. Entanglement is real, and there are no hidden variables. Two particles are genuinely connected in a way that cannot be explained by classical physics. Einstein was wrong, but there is an important point to clarify. Although the connection between two particles is instantaneous, you cannot use it to send information faster than light, because the result of your measurement is random. You cannot control whether your particle chooses to spin up or down. It decides for itself randomly. Therefore, even though the two particles communicate instantly, you cannot encode a message into that conversation. It is like two people at opposite ends of the galaxy flipping coins. Each result is random, but strangely, when one gets heads, the other always gets tails. They are perfectly synchronized, yet neither can use this to send a text message. Quantum entanglement is not just a scientific curiosity. It is being applied to real technology. Scientists are developing encryption systems that use entangled particles to transmit absolutely secure information. If anyone tries to eavesdrop, they will disturb the entanglement, sounding an alarm immediately. Entanglement is also the key to quantum computers. When many qubits are entangled together, they can perform complex calculations that normal computers could never do. There is even a phenomenon called quantum teleportation, not like interstellar travel in movies, but the ability to transfer a quantum state from one place to another using entanglement. It has actually been achieved in laboratories. The thing Einstein called spooky, the thing he refused to accept, is now becoming the technology of the future. Now, let us talk about another strange phenomenon, a phenomenon that violates every intuition we have about the physical world. In the ordinary world, when you throw a ball at a wall, it bounces back. If the ball is not strong enough to break the wall, it cannot pass through. Simple as that. But in the quantum world, a particle can do the seemingly impossible, appear on the other side of a barrier that it does not have enough energy to cross. Recall the wave function we discussed. The wave function of a particle does not stop abruptly at a barrier. Instead, it fades gradually through the barrier, like a whisper passing through a wall. Most of the wave function is reflected back, but a tiny portion still leaks through. This means there is a very small, but non-zero probability that the particle will appear on the other side. Scientists call this quantum tunneling. The electron looks at the wall and thinks, "That wall? I think I'll just take a shortcut." It sounds like a fairy tale, but quantum tunneling is a real phenomenon, observed thousands of times and used in everyday technology. For example, radioactive elements decay thanks to tunneling. Tiny particles inside the nucleus are trapped by strong nuclear forces. They lack the energy to escape. But thanks to quantum tunneling, sometimes they slip out. That is radioactive decay. Even the sun shines thanks to tunneling. In the sun's core, protons repel each other due to electric force. According to classical theory, they do not have enough energy to overcome this repulsion and fuse together. But thanks to quantum tunneling, sometimes they still fuse. The result is sunlight warming the Earth. Without quantum tunneling, the sun would not shine, and you would not exist. Finally, we arrive at perhaps the strangest idea of all, the idea of the quantum vacuum. What do you think empty space is? A place where there is nothing? No particles? No energy? No matter? Just zero? Once again, the quantum world says, not so. Remember Heisenberg's uncertainty principle? It does not only apply to position and velocity, it also applies to energy and time. This means that even in the emptiest space, energy can fluctuate for extremely short periods. These fluctuations create pairs of virtual particles, electrons and anti-electrons, photons, quarks, popping out of nowhere, existing for a fraction of a second, and then vanishing back into nothingness. The vacuum is not quiet. It is seething with activity. Scientists have found a way to prove this. There is an experiment called the Casimir effect. You place two ultra-thin metal plates extremely close together in a vacuum. According to classical physics, nothing should happen. But in reality, the two plates are pushed together by a small but measurable force. Why? Because between the two plates, only virtual particles of certain wavelengths can fit. Outside the plates, all wavelengths are allowed. The pressure from virtual particles outside is greater than inside. The vacuum presses the two plates together. This is practical proof that nothing is not actually nothing. Even if you remove everything from a space, something remains there. Energy fluctuations, virtual particles flickering in and out of existence. So, we have come a long way from superposition, which allows things to be both at once, to entanglement, connecting instantly across space, to tunneling, passing through impassable barriers, and finally to the seething vacuum, where nothing is actually something. All these strange phenomena lead us to a big question, a question that has kept physicists arguing for nearly a century. When do all these possibilities collapse into a single reality? Who or what decides which one becomes real? We have seen the electron existing as a cloud of possibilities, spreading through space in many places at once. We have seen the wave function evolve smoothly and calmly according to Schrödinger's equation. Everything seems reasonable in a strange sort of way. Then you place a measuring device. You look. You check. In the blink of an eye, that entire cloud of possibilities, the thing that had spread across space, suddenly shrinks into a single point. The electron is no longer everywhere. It is now times here asterisk. A specific location, a single result. Before measurement, it was an open mist, shimmering with potential. After measurement, it is a clear, solid dot. What happened in that moment? What caused this magical transition from maybe to certainly? How does the universe decide which of the infinite possibilities will become reality? This is not a small question. This might be the biggest, deepest mystery in all of modern physics. The problem is that no one knows exactly what triggers this collapse of the wave function. Is it the measuring device? Or is it the information being recorded? Does it require a consciousness, a human observer? Or would a fly flying by be enough? A single atom? A stray photon? Physicists have debated this for nearly 100 years. They have offered many different answers, many different interpretations. But the unique thing is that no one agrees with each other. Even today, scientists remain divided on this issue. Let us examine three main explanations, three completely different ways of looking at the same phenomenon. The first explanation, and also the most traditional one, is called the Copenhagen interpretation. This name comes from the city of Copenhagen in Denmark, where the great physicist Niels Bohr worked. Bohr was one of the founders of quantum mechanics. He spent years contemplating its meaning. His answer, simply put, is to stop worrying about what is really happening. According to Bohr, the wave function is not a real physical thing. It is merely a mathematical tool, a convenient way to calculate probabilities. It is more like a map than the territory itself. The map is not the actual country. It is just how we represent information about that country. Similarly, the wave function does not describe deep reality. It only describes what we can say times about the system based on what we know. When we measure, we learn new information. The collapse of the wave function simply means we have updated our knowledge. Bohr went even further. He said that asking where the electron is times before times we measure it is a meaningless question. It is like asking, what is the color of a trumpet sound? Or how does the number 7 smell? These are questions without meaning because they apply a concept to a situation where that concept does not fit. From the Copenhagen perspective, reality does not exist independently of observation. Where only becomes a meaningful concept after measurement. Before that, there is no answer. Not because we don't know, but because the question is invalid. This made many people, including Einstein, feel uncomfortable. Einstein asked Bohr, "Does the moon not exist when no one is looking at it?" Bohr replied cleverly, "Science does not speak about the deep nature of reality. Science only describes the results of the experiments we perform." This approach has an unofficial slogan: shut up and calculate. Do not waste time with philosophical questions. Just use the equations, get the results, and compare them with experiments. Does it work? It works. That is enough. This pragmatic approach helped physicists make rapid progress. They built atomic bombs, lasers, transistors, and computers, all based on quantum mechanics. The equations worked perfectly. The Copenhagen interpretation allowed them to use the theory without getting bogged down in endless philosophical debates. But that does not mean everyone was happy with it. Many scientists felt something was missing. They wanted to know what was times actually times happening, not just how to calculate results. In 1957, a young student named Hugh Everett was writing his doctoral thesis at Princeton University. He thought deeply about the problem of wave function collapse. Then, he had an incredibly bold idea, an idea that many considered insane. Everett asked himself, what would happen if the wave function times never times collapsed? Wait a minute, you might say, but we see it collapse every time we measure. We see a single result, not multiple results at once. True, Everett replied. You see one result, but what if all the other results also happened, just in different parallel universes? According to Everett's many worlds interpretation, every time a quantum measurement takes place, the universe branches. In one branch, you see result A. In another branch, a different version of you sees result B. Both results happen. Both are real. Only they occur in different parallel universes. Let us take a simple example. You measure the spin of an electron. It can spin up or down. According to Copenhagen, the electron is in a superposition until you measure. Then it chooses one of the two. According to many worlds, there is no choice at all. The universe splits in two. In the first universe, you see it spin up. In the second universe, another version of you, with all your memories and thoughts identical to yours, sees it spin down. Both versions of you are real. Both universes are real, but they do not interact with each other. Once branched, they remain forever independent. This idea sounds like science fiction. Parallel universes, infinite versions of yourself. Did Everett watch too many movies? But listen to the advantages. The many worlds interpretation is very clean mathematically. It does not need any special extra rules. It just needs Schrödinger's equation. The wave function evolves smoothly and continuously. Always. No sudden collapse. No exceptions. No magic. In a sense, it is simpler than Copenhagen. Copenhagen has to say, Schrödinger's equation works most of the time, but there is a special rule when measuring. Many worlds says, Schrödinger's equation times always times works. No exceptions. Furthermore, many worlds solves a philosophical problem. In Copenhagen, is there true randomness? The electron randomly chooses a result. But in many worlds, there is no randomness. Every possibility happens. The universe is completely deterministic. However, this explanation also has huge problems. First, it seems excessive. Every quantum measurement creates a new universe. Every second, trillions upon trillions of quantum events occur. That means the universe is branching continuously, ceaselessly, infinitely. The number of universes increases at a dizzying rate. Unimaginable. Second, it cannot be directly tested. By definition, you can never see the other branches. Once the universe splits, they never meet again. So how do you know they are real? Is this science? Or just philosophy? Third, what does probability mean in this theory? When we say the electron has a 50% chance of spinning up, what does that mean if both results happen? Everett had to redefine probability, not as the chance of something happening, but as the proportion of versions of you that will see this result. This works mathematically, but it sounds very strange. Despite these issues, the many worlds interpretation has attracted a following. Some prominent theoretical physicists support it. They argue that even though it sounds crazy, it is consistent with quantum math. Perhaps the weirdest thing about many worlds is that it could be true, and you would never know. In those infinite parallel branches, there are infinite versions of you, each believing they are the original, each living a slightly different life, never knowing of the other's existence. Copenhagen says the wave collapses. Do not ask why. Many worlds says the wave never collapses. Everything happens. But there is a third approach, a more subtle one, called decoherence. Decoherence is not a complete explanation of quantum mechanics. It does not answer if the wave function truly collapses, but it explains why we do not see strange quantum phenomena in our daily lives. The question is, why don't we see cats that are both alive and dead? Why isn't the table in two places at once? Why does the world around us look so classical, so solid, without superposition or interference? The answer lies in interaction with the environment. In the lab, scientists can isolate an electron, keeping it far from everything else. Under those conditions, the electron can maintain superposition, creating interference patterns, acting according to strange quantum rules. But a large object like a cat, or a table, or you, cannot be isolated. You are constantly interacting with the environment around you. Every second, billions of air molecules crash into you. Light bounces off your skin. Heat radiates from your body. Each of these interactions carries information about your state. When a quantum system interacts with the environment, it becomes entangled with the environment. Remember the concept of entanglement we discussed, where two systems connect in a quantum way. When a quantum system gets entangled with billions upon billions of particles in the environment, information about its state leaks out. The interference pattern, the sign of superposition, disappears. Not because the wave function truly collapses, but because it becomes entangled with so many other things that we can no longer see the quantum effects. There is a beautiful metaphor to understand this. Imagine you are walking on a frozen lake. Beneath the ice is liquid water, fluid, shifting shape, behaving in a strange quantum way. Above the ice is a solid surface, stable, predictable, classical. Decoherence is like the process of freezing. It does not make the water disappear. The water is still there underneath, but the ice layer hides it, creating a hard surface we can walk on. Similarly, decoherence does not remove quantum properties. They are still there deep down, but they are hidden by entanglement with the environment, creating the classical appearance we observe. The key is the speed of this process. For a small object, like a well-isolated electron, decoherence happens slowly. We can maintain the quantum state for a few seconds, even minutes. But for large objects, decoherence happens incredibly fast. Within trillionths of a second, it is so fast that the cat is never truly in a state of both alive and dead for a period long enough for us to observe. That is why the everyday world looks normal. Not because quantum rules stop applying, but because decoherence happens so quickly that we do not see the quantum effects. Decoherence also explains why quantum computers are so hard to build. You must keep qubits extremely isolated, at temperatures near absolute zero, avoiding all vibrations and all noise from the environment. Because if the environment touches the qubit, decoherence will occur, and the quantum state will vanish, like trying to keep a candle burning in a storm. But decoherence does not solve every problem. It explains why we do not see interference in large objects, but it does not explain why a specific result happens. When you measure an electron, why do you see spin up and not spin down? Decoherence cannot answer this. Some combine decoherence with Copenhagen. The environment causes decoherence, making superposition disappear practically. Then some unknown mechanism causes a true collapse. Others combine it with many worlds. Decoherence creates the branches of the universe, making them separate and unable to interact anymore. So we have three views. Copenhagen says reality does not exist before measurement. Don't ask more. Many Worlds says all realities exist in infinite parallel universes. Decoherence says quantum reality is still there but hidden by entanglement with the environment. Three views, three completely different philosophies. But the strange thing is that all three yield the same mathematical predictions. In most cases, all three work in the sense of giving the correct results. So which one is right? Actually, we do not know. Perhaps we will never know. Maybe this question lies beyond the capability of experimental science. But there is something even stranger than all three of these theories. An experiment showing that reality might depend not only on whether we observe it or not, but also on what we will do in the future. Time, it turns out, may not be as simple as we think. We usually think of time as a one-way street. The past has happened and cannot be changed. The future has not arrived and is undetermined. The present is the fleeting moment where the past turns into the future. Simple, clear, and logical. But the quantum world is about to break our common understanding once again. In 1978, a famous physicist named John Archibald Wheeler proposed a thought experiment that surprised, and even frightened, many people. He called it the delayed choice experiment. The idea is as follows. Let us go back to our familiar double-slit experiment. You fire a photon toward two slits. We already know that if there is no observer, the photon acts like a wave, creating an interference pattern. If there is an observer checking which slit it goes through, it acts like a particle, with no interference. Wheeler asked, what happens if you decide whether or not to place the observer times after times the photon has already passed through the slits? It sounds absurd. The photon has already passed the slits. It has already decided whether to act as a wave or a particle. Your decision times now times cannot change what happened in the times past, asterisk. But real experiments yield a different result. Scientists set up this experiment. They fired a photon through the slits. The photon flew through, heading toward the screen behind. In the very short time between the photon passing the slits and hitting the screen, they randomly decided whether to turn on the detector or not. The result? If they decided to turn it on, trying to see which slit the photon went through, there was no interference pattern. The photon behaved like a particle. If they decided not to turn it on, the interference pattern appeared. The photon behaved like a wave. Even though this decision was made times after times the photon had passed the slits, it is as if the photon knew in advance what you would decide in the future, and adjusted its past behavior to match. It is as if the photon could look forward in time, see what you were going to do, and then choose its path based on information from the future. This sounds insane. It violates every common notion of causality. the idea that cause must come before effect. How can a decision in the future influence an event in the past? The strangeness did not stop there. There is a variation of this experiment that is even weirder, called the quantum eraser. In this version, scientists do something clever. They tag the photon in a way that allows them to know which slit it went through. As expected, when path information exists, the interference pattern disappears. The photon acts like a particle. Then they do something remarkable. After the photon has passed the slits, and after it has been tagged, they erase the path information. They make it impossible to know which slit the photon went through, even by checking the data later. The result? The interference pattern returns. Think about this for a moment. The photon had already passed the slits. It had left a trace, and the information existed. But when you erase that information, even after everything has happened, the interference pattern reappears, as if the photon went back to the past to behave like a wave instead of a particle. Some explain this by saying reality is not complete until all information is determined. Not just information at the moment the event occurs, but all information related to that event, including decisions made later about whether to keep or erase the data. It is as if time is not a stream flowing from past to future, but a solid block, a complete picture where every moment exists simultaneously. What happens at one point in time can depend on what happens at another point, even if that point is later. Before you think you can send messages to the past or change history, we must clarify an important point. You cannot do that. Although the delayed choice and quantum eraser experiments show a strange link between past and future, they do not allow for the violation of causality in the ordinary sense. You cannot send a message to the past. You cannot change what has happened. Why? Because the measurement results are still random. When you look at individual photons, you see nothing special. Only when you collect enough photons and analyze them statistically do you see the interference pattern appear or disappear. Information about the future does not travel backward in a way you can use to communicate. It only affects how probabilities are distributed. It is like two people at opposite ends of the universe, each with a pile of photons. They cannot send messages to each other through those photons, despite quantum entanglement or delayed choice. The rules of physics still protect causality at the macroscopic level. But that does not make the experiment any less weird. It still suggests that our way of thinking about time fixed past, open future might not be how the universe actually works at the quantum level. There is another way to view these experiments. Information, not matter, is the true currency of the universe. In the classical world, we think of reality as physical things moving through space over time. Particle here, then there, then over there. Very simple. But in the quantum world, it seems reality is not locked in until information about it is complete. Not just information at a single moment, but all information relevant to the event throughout the system's entire story. A metaphor might help. Imagine you are watching a movie in real time. You see one frame at a time, from start to finish. But on the physical film reel, all frames exist at once. The 100th frame exists simultaneously with the first frame and the 1000th frame. Perhaps quantum time is like that. All frames, all moments exist together. What we experience is the viewing of one frame at a time, but they are not created sequentially. They are a solid block. From this perspective, The delayed choice experiment is not about influencing the past. It is about realizing that past and future are not as separate as we think. They are different parts of the same whole, connected in ways our ordinary intuition cannot grasp. We have come a long way in the quantum world, from Planck's simple energy packets through Einstein's photoelectric effect to the strange double-slit experiment, Schrödinger's elegant equation, and Heisenberg's uncertainty principle. We have seen superposition allowing particles to be everywhere at once, entanglement connecting instantly across space, tunneling passing through impassable barriers, and the vacuum seething with virtual particles. We have debated three different interpretations: Copenhagen with its pragmatic mystery, many worlds with infinite parallel universes, and decoherence as the bridge between two worlds. Finally, we have seen that time may not be as simple as it looks. The past might depend on the future. Reality might not be complete until the whole story is told. All of this is real, not empty philosophy or science fiction, all proven by experiments, precisely measured, and repeated thousands of times. The quantum world is strange, counterintuitive, and full of mystery, but it is also real, very real. Real enough that we are building technology based on it. Quantum computers, quantum cryptography, quantum sensors, all rely on these strange phenomena. Now, let us see how these weird principles are applied in the real world, how they are changing technology, medicine, and even how we understand life itself. Before we talk about specific applications, we need to change our view of reality one more time. Forget everything you thought about particles. Forget tiny marbles flying through space. In truth, there are no particles. There are only fields. This is one of the most profound shifts in modern physics, known as quantum field theory. It states that everything in the universe, every electron, every photon, every quark, is not a separate object. They are ripples in invisible fields spreading across space. An electron is not a tiny ball carrying a charge. It is a ripple in the electron field, an invisible field that exists everywhere in the universe. A photon is a ripple in the electromagnetic field. A quark is a ripple in the quark field. Imagine the universe as an infinite ocean. Actually, not one ocean, but many oceans layered on top of each other, each with its own waves. What we call particles are simply the waves on those oceans. The wonderful thing about this view is that it explains so much. Why can particles be created from energy? Because they are just waves. You can create a wave by disturbing the water. Why can particles disappear? Because waves can calm down. Why are there antiparticles? Because waves can oscillate in different ways. Forces are also the exchange of virtual ripples, tiny fluctuations in the fields, existing too briefly to be observed directly, but long enough to transmit force. You, right now, are not a pile of particles. You are a sophisticated pattern woven from countless ripples in the electron field, the quark field, and the photon field. You are a poem written in quantum vibrations, a melody in the grand symphony of the universe. Now, let us turn to the application that perhaps leaves the deepest impression: the quantum computer. A conventional computer is like a careful librarian. It turns every page of a book, reads every line, and processes information sequentially. A quantum computer is like a mad poet. It reads all the books simultaneously, with whispers overlapping, and somehow finds the answer amidst that chaos. The secret lies in the quantum bit. A qubit is not merely a 0 or a 1. Thanks to quantum superposition, it can be both 0 and 1 at the same time. 2 quantum bits can represent 4 states simultaneously. 3 quantum bits can represent 8 states. The number grows exponentially. With 20 quantum bits, you have over 1 million states. With 300, you have more states than there are atoms in the entire observable universe. That is the power of superposition. Quantum entanglement makes everything even more powerful. When quantum bits are entangled, they create complex connections that classical bits could never achieve, like dancers moving in perfect synchronization at opposite ends of the galaxy. But building a quantum computer is incredibly difficult. Quantum bits are fragile. The slightest vibration, a tiny change in temperature, or even a stray photon can destroy the quantum state. This is called decoherence, the number one enemy of quantum computing. So what is the solution? Freeze the system to near absolute zero, colder than deep space. Isolate it from all vibrations, and shield it from all electronic noise. It is like trying to keep a candle flame burning inside a storm. Then there is the problem of error correction. Normal computers can copy data to back it up. But in the quantum world, there is a rule called the no cloning theorem, which says you cannot copy an unknown quantum state. Therefore, scientists have to find clever ways to protect information, like wrapping a poet in layers of soundproofing so they can continue to recite poetry without being disturbed. Despite these challenges, progress is happening fast. Quantum computers could revolutionize many fields. In quantum chemistry, they could simulate molecules with unprecedented detail, helping to design new drugs, new materials, and more efficient batteries. In optimization, they could solve complex problems about delivery routes or resource allocation that would take normal computers years to finish. In cryptography, they are both a threat and an opportunity. A quantum algorithm known as Shor's algorithm could break most current encryption systems. But quantum cryptography also promises absolute security based on the laws of physics. In 2019, Google claimed to achieve quantum supremacy when their computer solved a problem that would take a classical computer thousands of years. IBM is also developing impressive systems. We are still in the infancy of this technology. Today's quantum computers are like the first computers of the 1940s. Big, noisy, prone to errors, and expensive, but the potential is infinite. However, there is something even more interesting than human-made technology: the possibility that nature has been using quantum mechanics for billions of years. Biology is often seen as the realm of warmth, wetness, and chaos. Quantum physics is cold, isolated, and delicate. These two worlds should not work together, but it seems they do. Take the migrating robin, for example. It flies thousands of kilometers, finding its way with incredible precision. How do they know the path? A bold hypothesis suggests they have a quantum compass in their eyes. In a protein called cryptochrome, there may be pairs of entangled electrons. When light hits them, they interact with the Earth's magnetic field in a quantum way. Basically, birds might actually see magnetic fields. Preliminary evidence supports this idea. Nature has solved a problem engineers are still struggling with: maintaining entanglement in a noisy, warm environment. Or consider photosynthesis, the way plants turn light into chemical energy. The efficiency of this process is nearly 99%, too high to be just random. Recent research suggests that energy in leaves might explore multiple paths simultaneously, using quantum coherence to find the shortest route to the reaction center. Like dropping a marble into a maze, but instead of rolling down one path, it spreads out like a wave, sensing every path, then choosing the optimal one. Even your sense of smell might use quantum mechanics. A controversial theory proposes that the nose detects not just the shape of molecules, but how they vibrate. Electrons in protein molecules might tunnel across the scent molecule, with the probability depending on the vibration frequency. Your nose might be a tiny quantum spectroscope. The weirdest rules of the universe do not stop at the laboratory door. They are in bird feathers, tree leaves, and your breath. Life has silently used quantum mechanics for billions of years. It just never told us. From strange principles to amazing technology, from labs to nature, quantum mechanics is not just abstract theory. It is the foundation of reality, working right now in every atom of your body. But there is one final question, the deepest one we need to answer. What does all of this mean? Einstein once famously said, "God does not play dice with the universe." He hated the idea of randomness. He believed the universe must be a perfect clockwork machine where everything is determined, even if we do not know it yet. But quantum mechanics says, yes, God does play dice, and he even enjoys the game. When you measure an electron, when you check its spin, the result is truly random. Not random because we lack information, not random because the machine is bad, but random built into the fundamental structure of reality. Before measurement, the electron does not have a defined spin state that we just don't know about. It is truly not decided. Only upon measurement does the universe roll the dice, metaphorically speaking, and pick a result. This sounds like chaos, but actually, it is a very special kind of randomness. Structured randomness. Quantum physics does not say anything can happen. It says, here is the exact list of what can happen, with exact probabilities for each possibility. The electron has a 50% chance of spinning up, and 50% down. Not 49, not 51, exactly 50. Even more amazing. When you calculate these probabilities with quantum theory, they match experiments to 12 decimal places. 12. This is an unbelievable level of precision. It is like rolling 100 dice. You cannot predict exactly what each one will show, but the total score of all 100, you can predict that with incredible accuracy. Random at the individual level, but extremely orderly at the collective level. There is something profound here. Randomness is not the enemy of order. It is a different kind of order. Statistical order. Probabilistic order. Moreover, randomness might be the engine of diversity, of creativity. Without quantum randomness, there would be no genetic mutations. Without mutations, no evolution. Without evolution, no complex life. No you. No me. Quantum randomness gives the universe choices. It opens new paths, new possibilities. In a purely deterministic universe, everything would play out like a pre-recorded movie. But in a probabilistic universe, there is always room for the unexpected, for novelty. Perhaps Einstein was wrong, not about the math. He knew the math worked, but about the philosophy. Maybe randomness is not a design flaw. Maybe it is the universe's most wonderful feature. Randomness changes how we think about prediction, about the future. But quantum mechanics changes something even deeper, how we think about the nature of reality. Let us return to Einstein's question to Bohr. Does the moon exist when no one is looking at it? In the classical world, the obvious answer is yes. Reality is objective. It exists independently of our observation. We are just explorers finding what is already out there. But the quantum world suggests something different. Reality, at the deepest level, is not fixed before measurement. The electron is not somewhere that we don't know. It truly has no defined position until we look. Observation does not just reveal information, it participates in creating the result. We are not just passive spectators watching the cosmic play. We are actors participating in the action, influencing the story by our very presence. This does not mean that positive thinking can change reality at will. We cannot think, I want to win the lottery, and have electrons suddenly arrange themselves to make it happen. The influence of observation is subtle, appearing only at the quantum level under precise mathematical rules, but it still holds deep implications. We and the universe are not separate. The observer and the observed are entangled, not just metaphorically, but in the literal sense of quantum physics. You are not just times in times the universe. You are times part times of it. Every atom in your body was once part of a star. Every breath you take contains atoms that once belonged to countless other beings. You are the universe experiencing itself. Quantum mechanics teaches us a lesson in humility. The world is not obliged to be easy to understand. It is not obliged to fit our intuition. Our intuition evolved to handle apples and rocks, lions and trees, things of medium size moving at medium speeds, not electrons and photons. When the microscopic world acts differently from our expectations, that is not the world's fault. It is the limit of our intuition. So what have we learned from a century of quantum discovery? Not just equations, not just technology. There are deeper lessons, spiritual gifts. The first lesson is about uncertainty, superposition, Heisenberg's principle, randomness. They all say the same thing. Uncertainty is not a bug. It is a feature. In life, we often try to eliminate uncertainty. We want perfect plans, clear schedules, predictable futures. But the universe at its deepest level says absolute certainty is impossible. Instead of seeing this as bad, perhaps we should see it as liberating. Uncertainty allows for newness. It allows for creativity. It allows life to exist. If everything were rigid and predetermined, the universe would be like a stone statue, beautiful, perhaps, but dead and unchanging. The second lesson is about possibility. Before measurement, the electron is everywhere. The photon goes through both slits. Possibility always exists. In the quantum world, nothing is completely impossible, only extremely unlikely. An electron can tunnel through a wall. Theoretically, all atoms in your body could simultaneously tunnel through a wall. The probability is near zero, but it is not zero. The universe is always more open than we imagine. There are always more possibilities than what we see at first glance. The third lesson is about connection. Quantum entanglement shows us that two particles at opposite ends of the universe can still talk to each other. Nothing is truly completely separate. The universe is not a collection of independent objects. It is a web of connections. Everything affects everything else, in ways we are just beginning to understand. The feeling of loneliness, of separation we sometimes experience, maybe they are just illusions born of our limited senses. At the deepest level, everything is woven together. The fourth lesson is about the question. Richard Feynman, one of the greatest physicists of the 20th century, once said, "No one understands quantum mechanics." He did not say this because he was unintelligent. He was a genius. He simply admitted that the quantum world is so strange it exceeds our ability to fully comprehend it. The wonderful thing is that this is okay. Not understanding fully does not mean failure. Sometimes the question is as beautiful as the answer. Sometimes mystery is what encourages us to keep exploring, to keep being curious, to keep wondering. A world we understood completely would be a boring world, but a world full of mysteries waiting to be discovered, that is a world worth living in. The final lesson is about humility. We often think we understand reality. We have clear concepts of space, time, matter, cause and effect. Quantum mechanics gently reminds us, not yet. You have only just begun. Our knowledge has limits. Those limits are not because we are stupid or lack tools. They are built into the fabric of reality. But that is wonderful. It means there is always more to explore. No matter how much we learn, no matter how technology advances, there will always be mysteries, wonders, and things that amaze us. All of these things, superposition, entanglement, randomness, uncertainty, what do they mean for your daily life? Perhaps not much practically. You still have to go to work, cook dinner, and take care of your family. Quantum mechanics won't help you find a parking spot or decide what to eat tonight. But spiritually, in how you view the world, it can change everything. It reminds you that reality is deeper, richer, and more magical than what the naked eye sees. The table in front of you is not a rigid object. It is a dance of countless quantum fields, vibrating ripples, particles flickering in and out of existence. It reminds you that you are connected to the universe in ways you cannot see. Every photon of sunlight touching your skin has traveled 8 minutes from a nuclear reactor 150 million kilometers away. Every breath you exhale contains atoms that may have once been part of a dinosaur, or Julius Caesar, or a distant star. It reminds you that uncertainty is not the enemy. Your life is not written in stone. The future is not fixed. There is always room for change, for choice, for new possibilities. These lessons might not change your daily tasks, but they can change how you feel about living, about being part of this strange, beautiful universe. So we have traveled a long road, from crazy questions about quantum coins, through world-changing discoveries, to deep lessons about the meaning of life. Now is the time to stop, breathe, and reflect on all we have learned. The quantum world is strange, but it is also real, more real than what our eyes see, more real than what our intuition tells us. It is the foundation of everything vibrating right now in every atom of your body. You are quantum. You are wave and particle. You are possibility and reality. You are part of the universe exploring itself. A cloud of probability observing, wondering, and existing. That is the final gift of quantum mechanics. A view of the world that is more magical, deeper, and more beautiful than we ever thought possible. Thank you. Thank you for spending your precious time on this little journey. Thank you for letting your ears hear. your mind think, and your heart feel. Thank you for believing in the strangeness, for being willing to sit still with the unknown, with the incomprehensible. If you have fallen asleep, that is wonderful. The quantum world will still be here when you wake up. It is not going anywhere. In fact, it is everywhere, in every atom around you, in every ray of light touching your eyelids when you open them tomorrow morning. If you enjoyed this journey, please like, subscribe, and share the wonder with those you love. Study and sleep needs your breath. Those small interactions help us continue to fly, to bring stories of the universe to more people. Study and sleep, where science meets dreams, where reality meets poetry. We send you these final lines. In the smallest world, certainty shatters, but in that shattering, beauty is born. Reality is not solid, but soft, not rigid, but shimmering and poetic. Maybe, just maybe, that is why it is wonderful. Wishing you a peaceful sleep, wishing you beautiful dreams, dreams of other worlds, other possibilities, other versions of yourself in infinite parallel universes. If the many worlds theory is correct, remember that even while you sleep, even when your consciousness drifts into distant lands, quantum fields still vibrate around you. They whisper the rules of existence. They weave reality one moment at a time. You are never truly alone. You are embraced in the arms of the universe, surrounded by invisible fields, connected to everything else in ways science is just beginning to understand. That is the final gift of quantum physics, the reminder that you belong here. You are an inseparable part of this magical cosmos. You are ripples in the quantum ocean. You are a poem written in vibrations. You are the moment the universe opens its eyes and sees itself. Good night, our dear friend. The quantum world, strange, beautiful, and incomprehensible, will still be here, always, forever, in every speck of dust, in every beam of light, in every breath. And that is the most wonderful thing